Today we're going to talk about solar energy, but before we start the conversation, I'm going to show you something that is related to composite materials. And I want to leave a video with Jose Ignacio. It's a very nice video that shows how wind turbines get repaired. And these are very large structures. They are made out of composite materials. And very often you have damage, surface damage. And this can be because of birds hitting the blades. It can be because of stones or any type of foreign object damage that could damage these materials. And the problem is that if you have a damage in a turbine blade, you have to address the problem right away. You cannot let that damage grow, because that could become a catastrophic failure in the system. So as you will see in the video, it takes a lot of effort. You have to stop the turbine. Somebody has to get up there 100 meters above the ground and literally go and manually try to repair the blade. And that's a very labor-intensive, very expensive process. So there is a lot of research going on trying to develop what we call self-healing materials. And in this case, the idea is that for a polymer matrix composite, you can embed microcapsules that may contain a resin, let's say epoxy resin, okay? And then you have smaller little bits that contain a catalyst. And as we had discussed yesterday, if you want to prepare epoxy, you have to mix 2 parts. And then it depends on the system. It can cure in a few minutes. It will cure in a few hours. But the idea here is that if you have a crack, which will be the result of damage, that crack will rupture some of these capsules containing the resin. Once the resin starts flowing, it will fill the cracks. And when in contact with the catalyst, the resin will cure, and it will become solid. And that is a way by which you can repair surface damage in these type of materials. So there is a lot of work going on in this area. And people have actually shown. So this is an example of an actual system. This is a scanning electron micrograph. This shows you the little capsules that contain the resin. You can make them in various sizes. And the whole idea is that as you make your composite, you will mix these capsules with the resin. And again, whenever you break the membrane, the resin will flow. And this is an example of how the membrane has been broken. The resin will come out and then fill a crack. So this is an area of active research. And again, the idea is that you can heal materials. This is a relatively crude approach. There are things that we can learn from biology, for example, in how to repair structural systems. But even though it's a fairly crude approach, this is fairly effective. And it works really well. Now, this only works if you have relatively small damage that produces cracks that you can fill with the resin containing these beads. If you have substantially larger damage where the fibers start breaking, then that's a different situation. You have to go literally cut a piece. And repairing composites is not trivial. This is one of the big challenges. At the end of the session yesterday, we talked about recycling composites. And this is probably one of the drawbacks of these type of systems. They are so engineered that it is very difficult to recycle and reprocess, and the same thing to repair. With a metal, you can weld, you can attach a piece. In these cases, you can use adhesives, but you have so much anisotropy in these materials that unless you do it right, you can introduce stress concentrations. Those stress concentrations can induce cracks. You have the wrong type of condition. So this is something that I want to share with you from yesterday's discussion. But today we're going to focus on solar energy. And we're going to start the conversation on what we have, how we started on Monday, just trying to put things in perspective. If you remember, these are our energy flow diagrams. This is for the US in 2012. If you remember, the US uses 95.1 watts, which is almost 100 exajoules of energy. And as we have discussed, solar energy is a very small component of the energy portfolio in the US. I had also told you, if you remember on Monday, that the good news was that we have doubled the power generating capacity using solar energy in the last 5 years. The bad news is that when you show this in a logarithmic scale, we're still 2 orders of magnitude below where we should be if we wanted to replace fossil fuels with solar energy. So it's going to take a long time, at least for countries like the US, other emerging countries. This is a good opportunity, and they should try to use solar energy whenever possible. The whole idea, as we discussed on Monday, is to replace fossil fuels. And this puts in perspective only 0.2% of the energy in the US comes from solar energy, and that compares it with fossil fuels. We also talked on Monday that it is possible to produce all the energy needed in the US from solar sources, okay? It is possible. And one way of doing it is to cover an area this big using solar panels. Now, these 3 terawatts comes from the fact that if you have 100 exajoules of energy for a whole year, that is equivalent to having a 3.1 terawatts power generating capacity. So if you were to cover this whole area with solar panels, you will be able to generate all the energy needed to keep the US going for a whole year, okay? So people say, well, why don't we do it? Well, it's a real challenge. This surface area is equivalent to 10 times the surface area of all the roofs in every building in the US. So if you take every home, every building, and you multiply that by 10, that's the amount of area that you will need to cover with photovoltaic panels to produce 100 exajoules of energy for a whole year. The same thing is with the highways. If you take all the highways in the US, all the roads, and you multiply that by 10, that's the amount of surface area that you will need to cover with photovoltaic panels to produce all the energy that is needed to satisfy the energetic needs of the US. And obviously, you can extrapolate this to the world. So if you were to cover 6 boxes of the same size, you will be able to produce all the energy needed on the planet, okay? So the question is, why don't we do it? And the answer for that is cost. You know, one of the reasons why we don't do it is because it's very expensive. And as long as people are willing to use coal, where the price of coal is very low, you know, nobody's going to have an incentive to start building solar panels and installing them to replace fossil fuels. It's a matter of dollars and cents. Now, we care about the environment. You know, we are very concerned about the future of the planet. But that's one thing. The other thing is, are we willing to pay 10 times or 5 times the cost of electricity by getting rid of fossil fuels? And that's a difficult question, you know, especially when we don't have a lot of money to spend paying for energy. So this is a study I told you about on Monday. I would really encourage you, and I'm going to leave this information with you, but I would really encourage you to go and download this document. This was prepared by Google. And if you remember in this document, they compare all the different sources of energy based on what's called the levelized cost of electricity, okay? This is a way by which you can compare apples with apples, how much it costs to produce electricity using either geothermal, nuclear, solar. This is concentrated solar, and we're going to talk about here in a minute. Photovoltaic solar, you could use wind turbines in the ocean, inland. And what you have here are data based on the 2010 when the study was first prepared, and then they have projections for 2020, 2030, 2040, and 2050. In most cases, you can see that the price of these technologies is going to decrease. And the assumption that is made in this analysis is that you engineers are going to come up with some innovative solutions to reduce the cost of these technologies. Some examples, for example, carbon fibers. We talked about carbon fibers yesterday. And I show you how we were using now lignin, which used to be a byproduct of the pulp and paper industry, to make carbon fibers. And by doing that, we can reduce the cost. So if you reduce the cost of fibers, then the cost of wind turbines is going to go down. Same thing here. I mean, if you talk to the chemists or the physicists or the electrical engineers, they may come up with a great idea for the next photovoltaic cell, and that will reduce the cost. So all the projections are that the cost of these technologies is going to decrease with time. And that is because people believe that engineers and scientists have the brain power to come up with innovative solutions to reduce the cost of these technologies, okay? So in every case, technologies will reduce cost with time. The problem is that if nothing happens with coal, in most cases, these technologies will continue being more expensive than coal. The only exception are photovoltaic panels. And the prediction is that by 2040, which is still ways to go, the price of photovoltaics is going to be lower than the price of coal, okay? And that's a problem. That's a problem. Now, there are things that we can do. On Monday, we talk about public policies and the importance of public policies. And one way that we can address the situation is, for example, applying a tax on fossil fuels. If you apply a tax on carbon, then all of a sudden the price of coal is going to go up. And then you can see that by 2020, most of these technologies are going to be more affordable than coal. And that's when the whole game changes, okay? So it's great about science and technology. It's great about innovation. You know, these people at Google and most analysts believe that innovation is really going to drive the cost of these technologies down, but it's not sufficient. We really need a commitment, especially from our policy leaders, to make sure that they put a cost on carbon so that now we can compare truly apples with apples, okay? So we'll talk about solar, and again, when we talk about solar, it's not just photovoltaics. We're going to talk about concentrated solar power. So what I'm going to do is I'm going to show you a series of videos, okay? And some of these videos may be repetitive. You're going to see the information 2 or 3 times. But I believe if you hear some concepts 2 or 3 times, you know, they're going to become seared in your mind. So let's run some of these videos. And some of these are going to be fairly basic. Some are going to be a little more detailed. I'm going to spend a little bit of time talking about the mechanisms by which photovoltaic materials operate. Okay. If you have questions, please stop me. We can go through this. So let's do this.
The sun is the vast source of energy. The solar energy that reaches the Earth in 1 hour is about as much as the total energy used by the planet for an entire year. Solar power drives our weather, fuels plant growth, and interacts with greenhouse gases to heat our planet to a temperature that sustains life. Today, we are harnessing solar power for heat and electricity using both direct and diffuse sunlight. Diffuse light occurs when particles in the atmosphere scatter some of the direct sunshine. The most intense direct sunlight is in areas that have clear skies and low humidity, but all 50 states can take advantage of solar power. Passive solar designs for buildings use floor and wall materials that absorb and store the energy from sunlight. They slowly release the energy as heat at night. We use solar hot water thermal panels to heat water for homes, offices, and swimming pools. To help provide electricity, we use 2 types of solar systems: concentrating solar power, or CSP, and photovoltaic, or PV. Concentrating solar power uses the sun's energy to create enough heat to generate electricity. Mirrors focus direct sunlight to produce very high temperatures that turn water to steam. The steam spins a turbine, which drives an electric generator. CSP systems can store heat during the day, and then use it to make electricity during cloudy periods, at night, or whenever people need it. Concentrating solar power works best as large-scale installations that provide electricity for entire communities, cities, or regions. Photovoltaic systems are another solar electric technology. Unlike concentrating solar power, PV can use diffuse sunlight as well as direct light. PV converts sunlight directly into electricity using specially engineered materials. PV can power applications having electrical needs that are very small to very large, starting small with solar-powered calculators and remote school crossing signals. Then applications can increase to homes and businesses, all the way up to the large-scale needs of a city. Today's solar technologies are proven, reliable, and increasingly affordable. Large-scale concentrating solar power systems have operated continuously provides an abundance of solar fuel at a low price. Zero. Better yet, this fuel will always be free. The cost of equipment needed for capturing the sun's energy and generating electricity has come down rapidly, while installations have increased dramatically. The sun is by far our greatest source of energy, and we're putting it to work. Solar power has benefited the United States and countries around the world, everywhere the sun shines.
Okay. So any comments about the video? What catches your attention when you hear the video? So there are two types of solar energy. Photovoltaics, concentrated, very good. The cost of fuel is free. I mean, the sun is going to be there shining for the rest of time. You can see the trend in the US, actually installations have been going up. I told you in the last 5 years, we have actually doubled the number of installations in the US. The problem is that you start with a very small number and you double that small number, is still a small number, okay? So we really need to do this in a much larger scale. So we're going to be talking about photovoltaics and also concentrating solar. So let me show you another video, and then we'll go through some details. And this is focused on photovoltaics. Well,
Years ago, the first solar cells were made of silicon, and today silicon makes up more than 3/4 of the rapidly growing worldwide photovoltaic market. But photovoltaic, or PV cells, are also made with other semiconductor materials. Why so many types of solar cells? This diversity is due to innovation. PV materials are improving, manufacturing costs are dropping, and PV applications are expanding. Balancing these three factors can meet demands for clean green power while creating more American jobs. Innovation means improving photovoltaic materials. Every PV material absorbs sunlight differently depending on band gap, which is a unique electronic property of the material. Some cells absorb sunlight within the first micron of material. Others need 100 times more material to absorb the same amount of energy from the sun. The sun's energy arrives as a combined spectrum of different wavelengths. Each color carries a different amount of energy. This makes solar cell design more complex. If the energy of the absorbed photon matches the PV material's band gap, then an electron-hole pair is created. If the photon has more energy, it still creates only one electron-hole pair, but the additional energy is lost as heat. If the photon has less energy than the band gap, it is not absorbed. Low band gap materials absorb most of the solar spectrum, creating many electron-hole pairs, producing a high current. However, PV cells with low band gap materials have a low voltage. High band gap materials absorb only higher energy photons, creating fewer electron-hole pairs, producing a lower current with a higher voltage. A solar cell's efficiency is the percentage of the solar energy shining on the cell that is converted into electrical energy. One way to increase efficiency is to use multiple layers to capture power from multiple wavelengths of light. Understanding the properties of each PV material allows scientists to improve designs that maximize the power of the cell. Innovation in PV also means lowering the cost of manufacturing. Crystalline silicon cells have high efficiency because they use very pure single crystalline silicon, which is expensive to manufacture. Multicrystalline silicon cells have lower efficiency, but they can be cheaper to manufacture because they use lower quality silicon, less energy, and simpler manufacturing equipment. Thin film solar cells can be made from materials such as cadmium telluride, copper indium diselenide, or amorphous silicon. These materials absorb light more readily than crystalline silicon, so they can be used in very thin layers that are less expensive to produce. Thin film solar cells are generally less efficient than crystalline silicon cells, but they can be cheaper to manufacture because they use less semiconductor materials, which are grown on glass or flexible foil. Finally, innovation means meeting different applications best suited by different types of solar cells. Today, PV devices produce power to meet the needs of utilities, businesses, homes, and consumer products. Large-scale installations can use a range of highly reliable PV technologies. Solar-powered satellites are more sensitive to power per pound. These high-efficiency solar devices can accept higher material and manufacturing costs to get more electricity from less material. Flexible thin-film devices are being installed in innovative ways, including incorporation into structures with complex shapes. Photovoltaics are here and now, and the diversity of PV devices is advancing as scientists improve PV materials and develop new manufacturing methods. More solar applications are emerging as these innovations make PV more affordable.